Hi, my name is Callie Hoka, and today we are going to go over the ATP pathways for CAP1. Here are just two kind of more detailed pictures. So the first thing we're going to go over is breaking down glucose and the production of ATP that comes from that. This is a graphic that shows all the different steps. It shows that you get 2 ATP up here, 2 ATP down in the citric acid cycle, and then that the NADH and FADH2s are created and how they transport hydrogen electrons to the electron transport chain. And this is just a more detailed citric acid cycle. So once the glucose is changed to pyruvate, then it goes into the mitochondria, is then able to be turned into acetyl-CoA, and then the oxaloacetate is required to join with the acetyl portion of the acetyl-CoA to create citrate and go through this citric acid cycle and cleave off the carbons as it goes. So these are just a little more detailed pictures. And then we have a little simpler diagram. If the glucose is starting as glycogen and stored, it goes through glycogenolysis and is turned into glucose. And then the glucose is then goes to 2-pyruvate. This glycolysis process creates 2 net ATP because it actually creates 4, but 2 went into the reaction, and so we end up with 2 net. And it also produces 2 NADH in the glycolysis. We then get 2-pyruvate, and the pyruvate is then transported into the mitochondria. So this dotted line here, everything below it is mitochondria, everything up here is the cytosol of the cell. So the pyruvate is transported into the cell and into 2-acetyl-CoA, and then the oxaloacetate then joins with the acetyl to create citrate to then go through this cycle. The citric acid cycle produces 2 FADH2s, 6 NADHs, and 2 ATPs. So altogether, when we add everything, we get 32 ATP. Now, an NADH is 2.5 ATP when the hydrogen electrons go into the electron transport chain, and the FADH2s is 1.5 ATPs. So when we do the math, we get these from each of these different substrates. So when we add all of the yellow numbers is how we get to 32. And so only 4 ATP come from substrate level phosphorylation, and we can see that we get 2 from the citric acid cycle, and we get 2 from glycolysis. And all of the other 28 are going to come from oxidative phosphorylation in the electron transport chain. So going on to fatty acid catabolism is the breakdown of the fatty acids, separating the glycerol from the fatty acid. If you have a triglyceride, triacylglycerol, we are just going to look at a single fatty acid, so we're going to skip to this part right here and only have one fatty acid. We're going to look at palmitate, but this just kind of gives a good overview of how it breaks down the glycerol and how that goes is turned into pyruvate and then goes into the citric acid cycle. And then the fatty acid, which is what we're going to follow, is going to go into the mitochondria, into beta oxidation, and then be turned into acetyl-CoA, so it can then also enter the citric acid cycle. So if we, the ATP yield from breaking down 1 molecule of palmitate, it is a 16-carbon fatty acid, so we're going to use 16 carbons. It's going to be transported into the mitochondrion of the cell from the cytosol. It's going to immediately enter beta oxidation. Beta oxidation is going to produce 7 NADHs and 7 FADH2s. And then beta oxidation is then going to produce 8 acetyl-CoA. There's 16 carbons, so it's about 1 acetyl-CoA per 2 carbons, so that's 8 acetyl-CoA. And then it's not on here, but the oxaloacetate, oxaloacetate is then going to combine with the acetyls to create the citrates to go through the citric acid cycle and cleave off those carbons and produce 24 NADH, 8 FADH2s, and 8 ATPs. We use the same conversion as earlier, and when we do all of the math, we get, these are the numbers we get. We add up all of the yellows, so all of these, plus the 8 ATPs that are produced, and we get a total of 108. 2 were used to start the reaction, and so we take off those 2, so we end up with 106 ATP per palmitate molecule of 16 carbon fatty acid. So ATP production in relation to intensity and duration of exercise. All of the different pathways are going to be working at the same time, but the kind of exercise, duration, intensity, those are going to really be the control. Those are going to control which pathway is going to be preferred at the given moment. So glucose is going to be the primary energy source at the beginning of exercise, or really, really high intensity, because it's faster to produce and you can get ATP quicker. Once we go through all of the blood glucose and muscle glycogen that we have available, we then have to change to fat being the primary energy source. It's a slower process because it's longer, but it does allow us to continue going, but our intensity will have to decrease. Exercise intensity will have to decrease due to the longer process it takes for the fat to go from the fat and then into the bloodstream and then into the muscle and then into the mitochondria. So it's a longer process. Limiting factors of ATP production, if we're looking at glycolysis, phosphofructokinase and the levels of fructose 1,6-disphosphate are limiting factors. If they're not there, we can't go through glycolysis. And then also the amount of oxygen available, because if we have a large amount of oxygen available, we're not going to need to go through the anaerobic glycolysis, because it can then take the rest of the pyruvates and turn them into the mitochondria, into acetyl-CoA, and through the Krebs cycle. So if we have a high amount of oxygen, then we don't have to go through glycolysis as much. And then the citric acid cycle, limiting factor would be the oxaloacetate, which is a carbohydrate. If it's not there, we can't go through that cycle because there's no way to turn that acetyl into citrate. So to then continue on through the Krebs cycle. When it comes to the breaking down of fat, hormones play a role and tell the body when to increase fat catabolism and when to start storing fatty acids again. So epinephrine and norepinephrine, if they increase in the body, they increase the body's catabolism of fats, breaking them down into fatty acids so that if we need energy right away, we'll be able to have it to use. Overview, let's move this, of the ATP pathways. They are all working at the same time, but just different circumstances and intensity of exercise and situations are going to cause one pathway to be more preferred at that time. High intensity exercise uses glucose mostly because it's a faster source of energy until that glucose is too depleted that it's no longer able to be the primary source of energy. Anaerobic glycolysis, just the changing of glucose into pyruvate, is a lot faster, but it only produces about 5% of ATP possible from glucose. So it's used when we don't have oxygen available and creates a little ATP, but it's not going to be enough to last very long because the pyruvate has nowhere to go anymore and just turns into lactate. It's not able to continue on into acetyl-CoA and into the Krebs cycle. So when oxygen is available, our body is going to want to be able to take that glucose all the way through to the Krebs cycle and into the electron transport chain so we can get all 32 of those ATPs that are available in the glucose. And is the preferred way if we have oxygen available while we're exercising. And then, like we said before, fat metabolism is not preferred immediately when we need energy because it takes longer to break down the fat and be able to use it. But it is able to be used during long intensity or high intensity. Once we've gone through all of our glucose and glycogen stores, we can then use fat and break it down. We'll just have to reduce our energy level and energy output when we're using fat as the main energy source. And that is all.